Okay, so good morning everyone, and good afternoon, Toro. It's my pleasure today to introduce Ahmed Elian, who will be presenting his thesis work. Ahmed graduated from Georgia University of Science and Technology in 2012 and has been with Muslim Institute since then. He began working on this project almost 14 months ago. And he's been working on a clocking architecture with tunable delays for a millimeter wave beamforming receiver. So with that, I'll hand over to Ahmed. So we'll keep the presentation will be about 45 minutes. We'll keep the questions and answers to the end. After that, we'll have about 10 minutes of Q&A, and then there will be a closed session with the committee. So Professor Natura is on the phone from University of Tokyo. So we'll try our best to make sure the voice on this side is clear. Tora, please let us know if at any point the voice quality is not good. Okay, with that I'll hand over to Ahmed. Okay, very good.
No problem. Yeah.
Bismillahirrahmanirrahim. Thank you, Dr. Ayman. Welcome everybody. Thank you for coming to my thesis defense titled Clocking Architecture with Tunable Delays for a Millimeter Wave Beamforming Receiver. It's a circuit design project in the area of mixed signal integrated circuit design. So let me start with the outline. First, I'll start talking about the motivation and problem definition. Then I'll discuss some architectural options for implementation of the system. Then I'll talk about some idealized system level analysis without any considerations of circuit non-idealities. Then we will start talking about some issues in the actual circuit implementation. After that, we will discuss how the transistor level implementation of the building blocks were designed. And then we will talk about the system integration and simulation results. Finally, ending with the thesis contributions and conclusions and future work. So let's start with the motivation and problem definition. Researchers are starting to explore wireless communication at millimeter wave frequencies. If you look at the state-of-the-art wireless standards, we find that they are using frequencies in the few gigahertz, lower gigahertz range to achieve data rates up to 3 gigabits per second. If we need data rates more than 10 gigabits per second, we will run into fundamental channel capacity limits, and we will need much more bandwidth. That's why researchers have started exploring the possibility of using millimeter waves. This band extends from 30 to 300 gigahertz. And the main issue with these in this band is that it's highly prone to atmospheric attenuation, which means that it can't be used for long distance communication. Which means that we have to do some short range line of sight communication. There should be some directionality in signal transmission and detection. And so it includes short range communication applications like radar systems, wireless sensor networks, wireless personal area networks, wireless HD, so on. So in order to make the radiation pattern in the shape of a directional beam and also be able to steer it and control that electronically, there is a technique called beamforming, where the beam is steered in the maximum power direction and controlled in an adaptive way. This improves the link budget and mitigates the multipath interference. There are two main techniques, conventional beamforming methods. The first one is phased array receiver, and the second one is true time delay as receiver. With phased array receiver, phase shift corrections are applied to the incoming signal from the different antennas in order to steer the beam, to form the beam and to steer it. In true time delay receivers, RF delay elements are used to steer the beam. Both of these systems have many limitations in the millimeter wave band. So this system was proposed by Dr. Ayman, where the beam steering takes place in the mixed signal domain, and instead of just delaying the signals themselves or phase shifting the signals, we adjust the instant at which the sampling clock samples the ADC data. This way, this has been shown to overcome many of the limitations of the conventional designs. And we can see here that the success of the system highly depends on the design of these tunable delay units with certain specifications. Otherwise, the system will not be feasible. And this is the topic of this research. So what is the required delay resolution of these controllable delay units? Let's consider this simple example of uniform linear array where we have two antennas separated by half wavelength. If we do simple analysis for the delay compensation needed at incoming angle of alpha of theta, we will find that the delay correction needed is sin theta divided by 2fc. We can use this equation to find what is the delay step we need for a certain beam steering range and at different frequencies. If you look at the first column here, if we seek beam steering resolution of 1 degree, we will need very small delay step, like 0.2 picosecond, and it gets smaller as the frequency increases and becomes really challenging. Also, but 5 degrees is also acceptable since the beam width is 10 degrees. So here we summarize the target specifications for the system. The operating frequency is in the few gigahertz range, comparable to the bandwidth of a millimeter wave, of a baseband millimeter wave signal. The delay step needed, by looking into the table in the previous slide, a reasonable value is 0.5 picosecond. The delay span is really small. We don't need very large delay span, but we will still desire to maximize it. The output clock jitter, it's important to minimize it because any error in the sampling time will translate into noise in the sampled signal. So we're targeting 0.5 peak maximum RMS jitter. And so also it's important to have low power consumption, 1 milliwatt maximum, since the system will be replicated for each channel in the system. The delay has also to be controlled digitally because the beamforming algorithm will be controlling this delay. And finally, the settling time is not critical. It depends on the desired beam steering rate, which does not have to be very fast. Applications of digitally controlled delay are much more than just beamforming. They include clock and data recovery, frequency synthesis, time interleaved LCA, and others. So let me get started with the architectural options in the system levels. Here, with the simplest system that can generate multiple delay values is just a simple cascade of buffers in open loop. Here the delay step cannot be smaller than the buffer delay, which is tau b. And this typical value of this is 20 picosecond in 65 nanometer, the fundamental minimum. So this is not good enough. This can be improved by adding fine delay control. We can modify the design of these delay buffers to make them reconfigurable, and some digital control will adjust the delay of a single buffer and make it in very small steps. The main problem with this kind of open loop designs is they're very highly sensitive to process voltage and temperature variations. So, for example, the process can make the transistors fast or slow, and this will very much affect the delay. So here comes the idea of delay clock. The main idea is that if you delay a clock by 1 period or 2 periods of the same clock, you will get a signal that's in phase with the original signal. So that's what the DLL does. We have a delay line, and the DLL uses feedback that generates an error signal that adjusts the delay of the buffers to make sure that the total delay is fixed at one clock period. So this gives more immunity to PVT variations. The buffer mismatch effect is reduced. Based on basic DLL architecture, one might suggest this adjustable delay architecture, where we just select one of the clocks available at the delay line taps and take it to the output. This has the same limitation of the first, the simplest design, since we cannot achieve sub-buffer delay resolution. So, the buffer delay is the minimum value is 20 picosecond, and we are targeting something less than 1 picosecond. So this cannot be good enough. A typical solution in architecture is to use direct phase interpolation. This circuit accepts two clocks and generates an output clock that has its phase somewhere in between the two, and this can be controlled. But this design have a disadvantage, like they usually end up with significant area and power. And also they need signal conditioning, and they use slow slew rate signal, and those signals are highly susceptible to jitter. So what are other possibilities of adjusting a delay in a delay loop? Let's consider this simple example where we have 5 buffers in a DLL. So the total delay will be 1 period, and so the delay of a single buffer, tau b, is the clock period divided by 5. If instead of taking the feedback from the last point, if I take it from the point which is before, we have now, the last buffer is now no more inside the loop, and we have only 4 in the loop, and so the clock period is divided by 4. So this gives us increment from 0.2 to 0.25, 0.05 reference period, which is less than the buffer delay. This idea can be used to generate to suggest another design where a loop multiplexer is used in addition to the output multiplexer, and it selects one of the delay line taps and takes it to the feedback. Depending on which tap is selected as feedback clock, the delay of the single buffer in steady state will be readjusted. But the main issue, this has some issues like nonlinearity. Since we are adjusting the denominator here, NL. NL is a very important quantity. I'll keep using this notation. It means the number of buffers that are actually inside the loop. And it depends on the delay control. So since we are adjusting the denominator, the delay will not change linearly with NL. Also, when you change NL, the loop will be disturbed and will need to settle again. And it might end up in false lock conditions. All of these issues have to be dealt with. However, can we even, here we can only achieve integer values, normally integer values of NL. Can we effectively or virtually achieve non-integer value of NL? Let's go back to the example. Here we have 5 buffers in DLL. And here we are taking only one feedback signal. What happens if we take 2 feedback signals and combines them in a certain way and to generate one error signal that controls the delay loop? Here we cannot say that the number of buffers is 5. We can't also say it's 4. It's somewhere in between. So we can say some virtual clock between these 2 clocks will be locked to the reference clock. Using this idea, okay, let's explain this in more detail. Here we have 3 cascaded buffers, and we have 2 successive taps from the delay line. The idea is to give each one of these a weight for its error. And in the end, in steady state, a virtual clock that depends on alpha, located between these 2 edges, will be locked to the reference clock. If you do the analysis for this, we will find, as we show here, that tau b will be T reference divided by NL, the same equation, but here NL has 2 components. The first component is integer, NLF, which depends on which points you are taking as feedback. And the other component is the interpolator ratio, alpha. So here you can adjust NL in steps of 1 over M. And M here is also very important to remember the meaning of this. It is the number of interpolator levels, or the interpolator resolution. Using this idea, we propose this architecture where a loop multiplexer is again used, but in this case it selects 2 successive delay line taps, takes them to the feedback, and generates error signal for each one, and combines them with the weights. It gives a weight for each one and combines them in a certain way, and uses the result to control the delay line. This way we can achieve delay values of N, reference period divided by NL, and NL here can be finely adjusted. The main advantage of this architecture, if we compare it to the direct phase, is here the interpolator design is would be much simpler than the design of a phase interpolator. Because here we are interpolating error signals, like this is some kind of amplitude rather than phase interpolation. And we will discuss several ways to implement this. It's also flexible in terms of what things can be designed. You can design the interpolator resolution, you can design the number of buffers, and other things. So now we start with some idealized system level analysis of the proposed architecture. This whole analysis is based on this simple equation, which we have presented, that the delay values available are integer multiples of the single delay buffer delay, and which is the reference period divided by NL. We use this kind of diagram to explain what is the set of delay values we can generate from the loop. The x-axis here from 0 to 1 is one reference period. Each point of these represents one delay value with respect to this reference period. And here in the y-axis we have the number of buffers in the loop. So, and each color represents a delay line tab. So we can know from each point what is the needed number of delay buffers, and if we count the curves, we can know which tab will give us this value, this delay value. Here, this is the case where we don't have interpolator, just a loop multiplexer selecting one feedback signal. What happens if we do add 3-bit interpolator and select 2 feedback signals instead of 1? We fill in the gaps basically, and we can vary NL and make it non-integer. In the first diagram, it can only take integer values. Here it can be non-integer. We have increased the number of delay values from 32 to 245. So here, this poses many questions. First, we can see that the delay step is non-uniform for sure. It's non-linear. If you want to maximize the delay step and in a small delay range, where should we locate this delay range? Also, we have assumed that NL goes down to 0. This cannot be practically possible. So what is the optimal minimum NL value? Where should we start? Also, it's very difficult to program this for certain delay value. So how can we make it simpler? And how does the delay step depend on N and M, the number of buffers, total number of buffers, and the interpolator resolution? So here we have done some analysis that showed that the highest density of delay values starts at the minimum buffer, the minimum delay at the first step, which is normal, the reference period divided by N. Secondly, we have shown that the optimal value of the minimum buffers, number of buffers in the loop, is N over 2. Because if we make it smaller than this, we don't get any improvement in the worst case delay step. So there is no sense in starting at 2 or 3. So we can start at 5 safely without losing any delay resolution. This way, NL has to vary from N over 2 to N, and this corresponds that the delay has to range from a certain value to double that value. This is essential requirement. Secondly, how do we make it easier to program this for a certain delay value? Here, it's very, very difficult actually to decide what NL value and what N value is needed for each delay type because of the overlap between the curves. You might need very high jumps and you might need to disturb the loop just to make small increments. So we propose dropping the overlap between these curves so that we only use one tab and we do fine adjusting of delay by adjusting NL and coarse adjusting of delay by adjusting N. This way we can see that the general trend in the delay step is increasing. So here we are comparing before we drop these delay values and after. Does this affect the delay resolution? Here we are plotting for different N and M values. We are plotting versus M and we are parameterizing N. And the dashed lines are with easy tuning. Dashed lines are without with easy tuning, and the solid lines are without. We can see that the difference is not even noticeable. So there is no any degradation in the resolution because of dropping the values and using this diagram. Also in this chart, we can see that we can achieve 0.2% or two parts in 1,000 of the reference period. So for 500 picosecond or 2 gigahertz clock, that's 1 picosecond. We can achieve that smaller than this by only 7-bit interpolator, for example, and 6 buffers, or just 5-bit interpolator and 11 buffers. So all of them are cheap options. So now I will start. So far we have been discussing the system level architecture without any attention paid to the non-idealities of the actual circuits, or how to implement the interpolator. And that's what we discuss now. This is the design that the idea came from. We found in the literature, design from UC Berkeley, where they do the interpolation in current domain. They use 2-phase detectors, and they control the tail current of each one of them, and to generate one combined error signal. And this phase detector drives a voltage to current converter, a voltage to current converter. But typically, what is used is a charge pump. So they are using 16 delay line buffers. They are using only 5-bit interpolator. They have achieved at tab 10 only. They have achieved a worst case delay step of 5 picosecond, and this design consumes 33 milliwatt of power, which is quite big at operating power at 1 gigahertz. So we think that much better than this can be done with this idea. But we prefer to work with a conventional or typical type 1 analog DLL. This typical configuration consists of 3 main parts: a phase frequency detector, a charge pump, and a voltage control delay line. This is the basic operation of a basic phase frequency detector. It has 2 outputs and 2 inputs, and it operates in 3 states. And ideally, the transfer characteristic of average output versus delay error is linear. When we use a phase detector, this enables the use of a charge pump. So what does adding the charge pump do? The charge pump is basically an integrator. We can see that a finite phase error between these 2 clocks generates current pulses, and these current pulses will keep charging this capacitor, making a ramp signal on the control voltage. So the control voltage will keep increasing. This basically means the gain of the gain of this feedback circuit is infinite, virtually infinite, and this will cause the steady state error to be 0. Otherwise, if any tiny error is there, this will not be settled. This will keep increasing or decreasing. So with this kind of feedback circuit, what are the options of implementing the interpolator? We can think about 4 possibilities: the input of the PFD, the output of the PFD, the charge pump currents, and the control voltage signals. The output of the PFD is really a digital signal, and the information is in the pulse width, it's not in the amplitude. So doing interpolation there would be somehow difficult. And also the control voltage signal cannot be used in interpolation directly, because it's not an error signal. When the interpolation is done, it has to be done on signals that represent the phase error. So this leaves 2 options: the input of the PFD. We just make a compounded clock before the PFD, or at the charge pump currents. We discussed these in more details. This is one possible implementation, where the interpolation takes place before the PFD. How does this happen? We select 2 delay line tabs, and we use some signalizer to make alternation in the clock edge selection. So for example, we select the first edge for 3 times and the second edge for 1 time, and so on. So the phase of the clock at the output of this multiplexer, 2-to-1 multiplexer, will not have uniform phase. It will have some pattern of phase, and the average of the phase error signal that will be generated by this circuit, by this phase frequency detector, will be somewhere in between the one that would have been generated by single feedback. So this has advantage that first, you will only need 1 phase frequency detector and charge pump, but you need some design of digital circuit here for the serializer, and delta sigma modulation can be used to achieve very high resolution. But this has problems since you are doing interpolation over time. This will cause slow periodic jitter, as we will explain more shortly. And the settling time will be quite large, especially if you have high delay resolution. If you want very high interpolator resolution. This is the other possible implementation where interpolation is done in charge pump domain, in current domain, using two charge pumps. We control the current of each of these two. We give so that the total current is fixed. So here we can see the first charge pump has a current of alpha I naught, and the other one 1 minus alpha I naught. The summation of these two is always equal to I naught. And depending on how much weight we give to each of these currents, the average phase error will depend on that. And this is possible actually because the charge pump, the current pulses generated by the charge pump actually do represent the phase error signal. This has advantage. Implementing things in current domain has the advantage of simplicity. Generating variable current and digitally controlled current is straightforward using a current DAC. Also, summing currents, you don't need any combining circuit. You just sync the two currents in one capacitor, and that's summation. Here we compare the two possible implementations that we have discussed. The interpolation at the PFD input and the interpolation at the charge pump currents. This is the timing diagram of these two, which we can see if the interpolation is done over time, the control voltage signal will have a slow ripple, low frequency ripple, and this will cause a slow periodic jitter in the clock. And this is very undesired. We want to minimize the jitter in the clock. But here, when we are doing interpolation current domain, the up current is first activated, and then the down current is activated every clock cycle. And what this causes is a narrow ripple in the control voltage, and this ripple has the same frequency as the clock. Since it has the same frequency, it will not cause time varying jitter. It will only cause some static, non-uniform error to the buffer delays. So we go with the second option, where the interpolation takes place in the charge pump currents. Let's have a closer look into this. Here we have a general interpolation example. This is the total current coming out from the two charge pumps. If alpha is small, this has to be wider and in steady state than this, so that the net current has to be zero. The average current has to be zero in steady state, so that the control signal is steady. And this is the ripple caused by the control, caused by this current in the control signal. If we solve the equation that the current on average has to be zero, we will find that the delay of a single buffer is the reference period divided by L, and L again has two components, as just the same case with the system with the same ideal behavior that we desired. So ideally speaking, this does the job of interpolation as we want it to be. So I'll skip this. This is just a technique to make sure that we don't end up in a false lock condition. We can come back to it if there's any question. Let me start now with the circuit implementation of the DLR building blocks, the phase frequency detector, the charge pump, and the voltage control delay line. By giving an overview of the simulation, we are doing only schematic level simulation, and we are using Global Foundries 65 nanometer low process enhanced process. We are using 1.2 volt supply and 2 gigahertz input clocks. One of the PFD designs that we found in the literature, one of the simplest designs is this dynamic design that based on so-called half-transparent register. The problem with such a design, we can see that if X lags Y, the output is idle. If this phase error between these two signals is very small, the signal will not be able to go down to zero. and will not be able to turn on the charge pump. Basically, not turning on the charge pump will result in a dead zone in the characteristic of the from the input phase error to the charge pump output current. So in this dead zone, the charge pump does not generate any corrective signal. And when we have a dead zone, we don't have basically filtering of jitter. So this is undesirable. How can we get rid of this dead zone problem? This is a very common phase frequency detector implementation that uses two edge-triggered recitable flip-flops. This is the function table of each one of these. The reset is asynchronous, so once it's activated, regardless of the clock, the output will be directly reset to 0. So in this case, we can see that regardless which of the two clocks leads the other, we will always have minimum pulse width, minimum width pulses at the idle output, which is the output which is supposed to be idle. This will make sure that the charge pump is turned on every clock cycle, even if the phase error is 0. And basically, what this does is it will eliminate the dead zone, since the width of these pulses can be adjusted in infinitesimal way. And this means that basically there will be no dead zone. But having these activating the charge pump every clock cycle will cause problems, like you will have more ripple in the control voltage, and you will have static phase error because of the charge pump current mismatch. This is the suggested design of the developed design of the phase detector, the D flip-flop used in the design of the phase detector. This is a true single phase, simple true single phase register, true single phase clock register, or TSPC register, and it's called single phase because it does not need the complement of the clock. It only needs single phase of the clock, so there is no worry about the clock overlap. And since the output here is active low and the reset is active high, so okay. This also shows how the design was developed. First, if we set D to 1, the reset is reduced to B, as we see here. And if we can add reset that can take action directly by discharging this transistor, and then this will be charging this directly, regardless of the clock. So this way we get a register with D equal to 1 and with asynchronous reset. And since the output is active low and the reset is active high, we can generate the reset signal using a NOR gate. This is the simulated transfer characteristic of the implemented TSPC based phase frequency detector. We can see that it's very highly linear, very close to the ideal behavior, and the average power consumption is low. It's only 36 microwatt at 2 gigahertz, and the minimum pulse width, or the reset pulse width out of the PFD, is about 100 picosecond. It was minimized by using low threshold voltage transistors, because the wider the reset pulse, the more effect current mismatch will make in the charge pump. So it's desirable to have small minimum pulse width. This is the charge pump implementation. The design was taken from the literature and slightly modified to enable the use of a PMOS current DAC. Since PMOS current DACs have better mismatch characteristics than NMOS current DACs, the advantage of this charge pump implementation is that first, the switches are connected directly to the output. There is no mirroring needed, and so it will have high speed. It's very desirable to have high speed charge pump. Secondly, the switches are not connected directly to the output, which means less capacitive coupling from the switch, from the parasitic capacitance to the output. So we try to minimize the ripple at the output. But it has a problem that the output resistance is not very large. The output resistance is not very large because these switch transistors will not be operating in saturation mode. They will be in triode mode, which means that there is no cascading of current sources. And this And when the output resistance is not very large, the output current of the charge pump will vary significantly with the control voltage. We have used also large length transistors, because with the larger length you get somewhat more output resistance. This shows some of the DC simulation results for the charge pump. Here, the current DAC current, which was just implemented by a variable current source, is swept, and we plot the output charge pump current versus the DAC. We can see it's fairly linear. The blue curve is when up is active, and the green curve is when down is active. Here, in the second plot, we are plotting the case where the output current from the charge pump when both up and down are active. So this ideally should be zero. But practically we can see it's non-zero mainly because of the output resistance of the charge pump. And it varies versus the control voltage. The mismatch varies with the control voltage because of the finite output resistance. However, by monitoring the flat region here in this curve, we can tell what is the range that is allowed, so that the charge pump is always properly biased. And it's about from 0.25 volt to 0.9 volt. And we have killed the mismatch at a certain point here, where the number of buffers in the loop is 14. Now this shows how the phase frequency detector was combined with the charge pump, and the direct outputs here are active low. Down is needed to be active low, so we use 2 inverters, and up is needed to be active high, so we need 3 inverters. This causes the difference in the numbers of inverters will cause a skew between up and down, and this skew eventually will translate into a ripple in the control voltage. So what we do here is we minimize the delay of these 3 inverters. We measure the input capacitance here, and we minimize it using the logical effort method. And this also, we manipulate some transistor sizes to try to equalize the delay of these 2 inverter chains. The simulated charge pump rise time was about 25 picosecond, which is less than the minimum pulse width of the phase frequency detector, which means that there will be no dead zone. Here we show the design that we adopted of the voltage control delay line. This was found in the literature. First, we have considered many capacitive control delay lines where you just control the output capacitance of a simple CMOS inverter. But we have found that those designs are very difficult, cannot be used to achieve delay range from X to 2X, which is our desired requirement. So that's why we considered resistively controlled delay lines. Resistively controlled delay lines have problems. The dead band, so-called the dead band problem. So let's consider this circuit from the literature and let's ignore this weak inverter connected in parallel. If the control voltage approaches zero, or if the control voltage approaches zero, these transistors will become in cutoff mode, and this means that the signal here will die, and the delay will go to infinity. But adding this weak inverter, this will put a maximum limit to the delay of the voltage control delay line. So that when these transistors go to cutoff mode, these inverters take action and actually limit the delay to a certain amount. So we use this schematic of voltage control delay line, and here we show the simulation results for the transfer characteristic. The first plot here shows the delay of a single buffer, and here we have the delay of 14 buffers in cascade. So this simply shows that we are achieving the desired delay range from 500 picosecond to 1000 picosecond, which is 1 nanosecond, in the allowed delay, control voltage range from 0.25 to 0.95. These limits are imposed by the charge pump. The control voltage range should not be outside, so that the charge pump is always properly biased. Now let's start with the system integration and simulation results. This is a screenshot from Cadence showing the system. We have 14 voltage controlled delay line buffers, and we have 2 phase frequency predictors and 2 charge pumps. The design of the loop multiplexer and out multiplexer is based on transmission gates in parallel configurations. We didn't use 3 configurations since it will cause more delay. We don't want a large delay for the multiplexer. We're also compensating for this multiplexer delay here on the other side by adding some similar circuit. Also, we are maintaining the symmetry in the load each of these delay stages C. And so that we can see that the first delay line, the first 6 buffers are connected to the output multiplexer, and the remaining buffers are connected to the loop multiplexer. And the last buffer is also connected to a dummy delay unit so that it sees all of the buffers see the same load. Here we show the functionality of the system. We compare the ideal behavior with the simulated behavior in the 50% interpolation case. When we have 50% interpolation, ideally, the reference clock edge should be midway between the 2 feedback clock edges. As we should see here, it's in the middle. We can see it's somehow close to the middle point. We can see that also the charge pump has to activate up, then down. Here, it's the opposite. First, the current goes negative mainly, and then positive. And the reason for this is that in the second one here, we have assumed a positive gain voltage control delay line, which the actual delay line used will have negative gain. We can see also the ripple is somehow a little bit similar in triangular shape in the control voltage. One thing of significant importance is the amount. What is the optimal value of the charge pump capacitor? The dynamics of the loop will highly depend on this. So here, what we do, we sweep the charge pump capacitance and we plot the jitter of we measure the jitter in the delay line plots. So we can see 2 phenomena. For very small capacitance, the jitter increases with smaller capacitance, and when the capacitance goes also very large, the jitter also starts increasing again, and there is some minimum in between. We can explain this by considering 2 sources of jitter. The first source here is the delay line generated jitter. This is high pass filtered by the loop, and if you have larger charge pump capacitance, less jitter will be filtered. That explains the slow increase for large capacitance value. And here we show the effect of the noise in the charge pump current, and this is multiplied by the gain, which is 1 over C. So with smaller charge pump capacitance, the jitter increase is significant. However, the value that we choose for our design is not the optimal value in terms of jitter, but close to that value, which is 216 femtofarad. And the reason for this is to minimize the settling time and the simulation time. If we choose one of these capacitors, the simulation time will go very large because the loop will take a long time to settle. And we are only sacrificing maybe 20 femtosecond of RMS jitter, so no problem. Here we are comparing the delay values that we get ideally with what we actually got from this architecture. The solid lines here, this is the same diagram that we discussed before. The solid lines here represent the ideal values, and the dashed lines represent what actual values we have got. We can see that there is a little bit deviation from the ideal value, especially if the number of buffers goes down to 7. And the reason for this is the charge pump mismatch was killed here at NL equal to 14. And here it is maximum at NL is 7. This causes the log delay error or the steady state phase error to be zero, almost zero at 14, and it increases in magnitude as NL decreases. So this explains this deviation, and it could be easily redesigned to reshape these curves. Here we are. So now let's focus on the delay values on the first step only. Here we are plotting the delay values on the first step versus NL. So we can see the delay span we can get from the first step only is about 25 picosecond, and this is more than sufficient for millimeter wave beamforming receiver. Here we are plotting the delay step versus the number of loop buffers. We can see that we have a worst case step of 0.3 picosecond with 7-bit interpolator, and 0.4, it degrades to 0.4 with 6-bit interpolator. And we can see the main limitation on the worst case jitter happens at integer values of NL. So why is this the case? We explain this by referring to this timing diagram here, how we would expect the interpolation ideally to happen. We can see if alpha is too small, which means that we are very close to one of these integer values, this current pulse becomes narrower, and practically it cannot reach the full scale value, in such a narrow, small time. This is what causes this deviation from the ideal behavior, and we get the limitation in the worst case step near the integer values of NL. So here we compare the ideal and simulated worst case delay step. If this is not happening, these spikes here, we would expect 0.08 picosecond, but what we got was about 0.3. However, the best case step, which is here, is very small, even smaller than the ideal value. This 0.3 picosecond step would translate into beam steering resolution of 5 degrees and a plus minus 40 degrees steering range with a carrier frequency of 112 gigahertz, which is a millimeter wave carrier frequency. Here we show the simulation results for the power consumption. We can see two phenomena. First, there is a general increasing trend in the average consumed power, and there is as NL increases. And the reason for this, when you have more buffers, you need smaller delay, and smaller delay needs more current. This explains why the power increases. Also, we can see another phenomena that when you have fractional NL value, you have more power generally than when you have integer NL value, and this is caused by the charge pumps. When we have interpolation taking place, we have two charge pumps active, and they will consume more power. However, this excludes the power in the parasitics, since it's only schematic level simulations, and there are some missing parts that haven't been designed, the DAC and the biasing circuit for the DAC, to be precise, and the digital driving circuit. However, this digital driving circuit, all of these will not be considerably contribute to the power. And we have met our target specification of 1 milliwatt. Here we are plotting here we are putting the random jitter versus NL and the tap number. The random jitter is seen to decrease with larger NL because of smaller current in the voltage control delay line. And here there is some the ideal square root law that we would expect of the random jitter versus the tap number. The worst case jitter here is at the first tap is only 0.2 picosecond RMS, which is a very small value. Some eye diagrams of the jitter. Okay. Here we are showing how does the delay vary with the process and supply voltage. Ideally, since we are using a DLL, the main point of using a DLL is to minimize this variation. But however, we still get this variation. And the reason for this is the DLR does not guarantee exactly 1 period delay because of some non-idealities in the circuit, like especially mainly contributed by the charge pump current mismatch. So these results here are for the delay at tap 1, and here we have the delay span variation. The delay span variation is about 10 picosecond over different, from the worst case to, or the worst case delay variation is about 10 picosecond, which is less than the absolute delay variation. So is this too bad? We compare here, we do comparison between what if we use the voltage control delay line in open loop and fix the control voltage. What will happen to the variation? We can see even the results for the variation are not very satisfactory. However, it's still better than open loop variation. Here you have a variation over a process and voltage of about 16.6, and here it's, in the open loop case, it's about 30 picosecond. Finally, discuss the conclusion and future work. This is a comparison to the state-of-the-art architectures. We have used the 2 GHz operating frequency, 0.3 picosecond delay step. This number is quite small compared to the literature. The smallest number we find in the literature is the one here in yellow, where the delay step is 40.7 femtosecond, very small. But if we compare it to the peak-to-peak jitter, peak-to-peak jitter is about 34.4. Additionally, this design consumes a lot of power compared to our consumed power. So 15 milliwatt versus 1.5 milliwatt. And we can see the 1.5 milliwatt is very small compared to the literature. Also, the jitter specifications are very good. Here, we compare with the similar design that was done in UC Berkeley that I've talked about before. They are using 14 buffers. We are using 14 and they're using 16. So here, the green side is the better side. So we can see we are operating at higher operating frequency. We are achieving less delay step, smaller delay step in the same conditions. And the delay range is also larger in our case. And the worst case RMS jitter is also smaller. The power consumption is very much smaller. The system was consuming 33 milliwatt compared to 1.5 milliwatt in our case. Here, so here we have assumed 7 bits, and here we are assuming 5 bits, and still the specifications are better for our design. Conclusions. So the main design strengths are, as we have seen, the low power, low jitter, high resolution, and simple components. And it has high immunity, and the immunity to PVT variations is not very satisfactory. However, it's still better than the open loop case, as we have seen. The results prove that this design choice is very good for the target application of millimeter wave beamforming receiver. However, we have also shown in system level analysis that it is very adaptive, that it can be used for any design, for any type of application. And we have seen that the charge pump does not guarantee zero phase error because of the charge pump current mismatch. And this is very important to minimize this mismatch. And the main limitation in the delay resolution we can get is imposed by the charge pump speed. Some future work that could be done. So this design can be seen as a prototype, and still it has lots of room for improvement. However, it's promising in terms of power consumption, jitter, and delay resolution. And we can see there's much room for improvement, especially in the charge pump design. We have used a basic charge pump design, and still the specifications were good. So it's worth improving the charge pump design. Of course, towards a complete fabricated system, what is missing is to design a current DAC, to design a digital driver, and to do the layout, post-layout simulation, tape out, and experimental measurements. These are some important differences. So, in the end, I would like to thank Dr. Ayman Shabra for my advisor for the enormous amount of help and for the many lengthy, in-depth discussions and for helping me with every detail in this work. I would like to thank Dr. Gerald Yu and Toro for dedicating their time for evaluating this thesis. And I would like to thank Faculty of Microsystems Engineering in general, especially Dr. Ayman, Dr. Gerald, Dr. Abe, for the priceless knowledge that they have offered us. I would like to thank Semiconductor Research Corporation for funding this work, for funding this research project. Also, I would like to thank Master Institute and Abu Dhabi government for giving me this chance. My blessed family, I worth nothing without them, especially. And I would like to thank my friends, colleagues in Microsystems, and everyone who offered help, Sami and Mustafa for some technical support and guidance. Thank you very much. Alhamdulillah.
Thank you very much. So we have a few minutes for questions, so we can take questions from the audience.
Yeah, so my question about how dependent is this design on the technology? So what do you expect will change when you go to a smaller technology, the next technology node, for example, in terms of power and maybe also stability?
Well, generally, when you go to smaller, to more advanced technology, you have higher speed of operation. This will improve the specifications. The delay resolution expected to increase because it was limited mainly by the speed of the charge pump. Also, of course, when you go to smaller technology, you have smaller power. So always going to more advanced technology improves the specifications.
And if there's questions from the audience, any more questions? If not, then let's thank Ahmed again. Thank you, Ahmed. Now we will, I think, go into the closed session with the committee members. So thank you very much for attending.
Thank you so much.
And,
Can I have some chocolates, please?
Yeah.